Hello, everyone, and thank you for tuning into my talk. My name is Paul Rogozenski. I'm pleased to be part of the Neutrinos from Home 2024 conference. Today, I'll be presenting some preliminary investigations in collaboration with Jesse Muir at Perimeter and Arca Banerjee at Pune, validating sterile neutrino modeling for photometric large-scale structure surveys. In this analysis, we're going to use cosmological observables to constrain the properties of a potential sterile neutrino in our universe. We're going to consider a sterile neutrino that was once in thermal equilibrium with the early universe, so we call this a thermalized sterile neutrino. We're considering this sterile neutrino to be on the order of an EV mass, and its temperatures parameterized by delta N effective, which is the change in the number of effective degrees of radiative freedom in the early universe. The standard N effective is 3.044 from the standard neutrinos in the early universe, and now we're going to consider a little bit of extra relativistic degrees of freedom due to the sterile relics temperature. In the late time universe, its energy density is given by this green boxed equation here in the middle, which is analogous to what we've seen for active neutrinos, except now we have an effective mass. This effective mass captures the temperature dependence now of the sterile relic as well as its mass. So we add this additional parameterization here through this, its physical mass is m nu thermal and through delta N effective. So going from the early universe to the late time universe, the sterile neutrino is no longer relativistic, but rather cools along with the expanding universe and becomes non-relativistic. And because its thermal motion is so large, these particles are able to freely stream at a certain scale or below a certain characteristic scale. This is given here at the bottom green box down here, where you can read more in Georges and Pasteur from, for example, 2014 or their neutrino cosmology textbook. And there have been some pretty amazing constraints on the sterile neutrino and its potential properties using cosmology. Here's an example from a Jouet work from 2021, where assuming the minimal possible temperature scenario for a sterile neutrino that could have ever been in thermal equilibrium with the universe, they place joint cosmological constraints on its properties, particularly this mx, which is its thermal mass. What I'd like to note here is that photometric surveys can actually further constrain the physical mass of a sterile relic. Take, for example, the red and the green contours that you see in this triangle plot. What we're adding here is galaxy survey information from CFHT lens, and we can see, at least, which is more obvious in the 1D posterior plot here of MX, the transition from the red to the green for MX is very large. And they note that having this additional galaxy information really helps to constrain the mass of the sterile neutrino. So let's think about the physics for a second. If we wanted to use observables in the early universe, well, these sterile neutrinos behave a lot like active neutrinos. They shift and amplify the temperature peaks of the CMB, the temperature-temperature correlation function. And in the early universe, when the BAO is forming, it actually induces also a phase shift depending on its temperature and modulates the amplitude of the BAO peak. We're going to focus a little bit more on late time observables and the impact that these sterile neutrinos have on large-scale structure formation. Because of their large thermal velocities and their mass, they can lead to an overall damping of the small-scale matter power spectrum, which in turn hinders halo formation and reduces galaxy clustering on small scales, and even decreases void clustering statistics towards small scales. So the DSY3 extended models analysis considered such a thermal neutrino with different priors on either delta N effective or the physical mass of the sterile neutrino. Here's one such prior that was considered, which puts a lower bound on the possible temperature of the sterile relic, enforcing this the fact that it had to be in thermal equilibrium with the early universe. Using only the linear scales of the power spectrum, we were able to place in a joint analysis 3 times more stringent constraints on M effective. Depending on the prior, we were able to extract information on S8, or the clustering of matter at 8 megaparsec scales, weighted by the total matter energy density. And this is pretty interesting because depending on the priors that one chooses, one can shift S8, again with this suppression of the small scale power spectrum from the sterile relic, and possibly alleviate some tensions in essays. You could see the H-Naught Olympics, which is linked below, that investigated this further. And sure, we see this in 1D parameter space, and if we looked at some tension metrics, either evidence-based metrics or delta chi-squared kind of metrics, we see that there could be up to substantial preference for sterile neutrino in our universe. Substantial being defined by the Jeffrey scale, of course. If we look at the evidence ratio L and R, over here to the left, each one of these plots are designed such that if you go further to the left, one prefers the extended model cosmology. If you go further to the right, one prefers the standard model, lambda-CDM. And we see a somewhat similar story across these different constraints here. If we have this extra sterile relic with some mass, there seems to be some slight preference for this model over lambda-CDM. And with that data that we have, we want to improve this constraints and extend the analysis beyond the linear regime. To do this, though, we need some important modeling tools. We need to determine the limits of our nonlinear power spectrum models, and we need to determine the limits of our galaxy bias models. And to do that, we need cosmological n-body simulations with sterile neutrinos. The first problem I'll introduce is validating our model for the scale-dependent galaxy bias. I won't go into too much detail here, but you can check out my talk from Cosmology from Home from last year, or check out my paper that came out last year in the archive. Where it gets trickier is determining the validity of the nonlinear power spectrum. We need to figure out which prescriptions that exist currently can capture sterile neutrino cosmologies and to which scales they are valid. We're going to investigate two separate prescriptions, one being HaloFit, which was trained to n-body simulations using the lambda-CDM cosmological parameters to predict the amplitude of the nonlinear power spectrum. And we're also going to consider the newest edition of HM-Code 2020, which considers a more general scaling through a fractional neutrino energy density. And we're going to compare these prescriptions to evaluations of nonlinear power spectra from n-body simulations. We're going to run these simulations assuming different sterile neutrino cosmologies, a fixed lambda-CDM cosmology, but varying the neutrino properties of the temperature and its mass. We're then going to run these n-body simulations and compare them to late-time power spectra predicted by both HaloFit and HM-Code. We will also determine the halo bias from these n-body simulations and use what we find there to compare to our linear galaxy bias prescription and determine its validity as well. These are preliminary investigations, so we're going to be running these simulations that are mostly shot noise dominated at the very smallest scales and 1 gigaparsec per h cubed volumes. To generate the initial conditions for our code, we modify NGen-IC, which takes a power spectrum at an earlier time and creates a particle distribution for the n-body simulation, and REPS, which takes a late-time power spectrum and rescales it using scale-dependent fluid approximations and taking into account some relativistic effects that are ignored in n-body simulations. So to make that generation of initial conditions and running of the n-body simulation a little more clear, we have a modified figure here from Fiedler and Klang-Johann, 2018, which visualizes this process. At late times, so around z of 0, we want to ensure that our n-body simulation at the largest scales matches the linear prediction. So we start with a linear power spectrum prediction today from some sort of Boltzmann code evaluation from class or chem. We then scale back that initial power spectrum to the starting redshift from our n-body simulation, and that is done with REPS. Because neutrinos induce scale-dependent growth, REPS takes this into account in their two-fluid approximation scheme to rescale the initial the late-time power spectrum to the initial z is equal to 99 power spectrum for the simulation. And GenIC then takes this initial power spectrum and creates the particle distribution as well as the velocity distribution of these particles at early times. And then we use Gadget 3 to take that initial distribution and let these particles form under the force of gravity in this Newtonian nonlinear n-body simulation. And over here is where we read in the power spectrum or determine the power spectrum using a code called Phylanes 3. So what are some of these preliminary results? Here we have two nonlinear power spectrum. Both evaluated at the same physical mass of m thermals 1 eV, one with a standard neutrino temperature of delta N effective is equal to 1, and one with a much larger temperature, delta N effective is equal to 6. The black lines in each of these figures represent the simulation's total matter power spectrum. And we compare to, as I said, two different fitting functions. One with CAM plus HM code 2020, which is the red solid line, and class plus halo fit, the Takahashi halo fit, which is the blue solid line here. We also, for reference, plot the linear power spectrum evaluated from these Boltzmann code, the level of shot noise, and the free streaming scale, where at larger K, we expect these neutrinos to be fully free streaming particles. And at first glance, it seems like we're doing pretty well. Sure, with the delta N effective is equal to 6 case, we have some larger divergences at larger scales, but one can expect that this could be a breakdown from the nonlinear power spectrum prescriptions when exploring a non-standard lambda-CDM case. So we then look at ratios of the simulation total matter power spectrum to the predicted power spectrums from the nonlinear fitting functions, and we see even larger divergences. In particular, we see this approximately constant offset in the 1 eV delta N effective is equal to 1 case over here on the right, where we're comparing in red the simulation to HM code, and in blue, we're comparing the simulation to halo fit. So halo fit seems to want to diverge rather quickly, but HM code seems to have this constant offset, which is a little interesting. And when we look at this large temperature scenario, we seem to be completely off with both prescriptions. But there is a light at the end of this tunnel. What we're considering now is a ratio of ratios. Bear with me. What we're doing is taking the ratio of the CDM plus baryon power spectrum from the simulation to the total matter power spectrum of the simulation. That is in the numerator. In the denominator, we have the same ratio of the CDM plus baryon to the total matter power spectrum as predicted from HaloFit and from HM code. What this test aims to do is to see whether or not these codes predict an identical shape of the power spectrum, whether or not the power spectrum is increasing or decreasing at the similar scales as evaluated from the n-body simulation. And it seems like in the case for HM code, it is. It seems that HM code is predicting the proper shape of the power spectrum, but not the proper amplitude of the power spectrum. So this is an interesting case here, and one that we're going to be digging into a little bit more. One such case is degeneration of the initial conditions. So when we scale back that initial power spectrum as z is equal to 0, scale it back to z is equal to 99 to evaluate this n-body simulation, we take advantage of this REPS code. And REPS, the two-fluid approximation, evaluates the Euler continuity-Poisson equations to rescale the power spectrum from z is equal to 0 to 99. One important aspect of this code is that it requires the sound speed of the neutrinos. Now, sound speed is defined as the response in pressure to the response in energy density due to neutrinos. And it's given by this function down here when one evaluates the Fermi-Dirac distributions in this limit. And this is the mathematically proper way to do things. One investigation that I took is to, instead of using the sound speed of the neutrinos, use instead the average thermal velocity of these sterile neutrinos. Now, this is only a difference of about 17% in this case. And they have very similar functional forms. Really, the only difference is the amplitude. And we're going to be looking at some ratios here of what reps rescales the initial power spectrum to at z is equal to 99 versus the class prediction of the linear power spectrum using the full evaluation of the Boltzmann equations, so assuming no fluid approximation whatsoever. In blue, we have the original prescription using the sound speed, and in orange, the new prescription using the thermal velocity. To guide the eye, we also have two vertical lines here, one being the free streaming scale of this sterile neutrino at z is equal to 99, and the free streaming scale at 0. And we see that the initial prescription seems to have some artifacts here of the free streaming scale at these two different times in their rescaling, whereas when one takes into account and rescales with the thermal velocity, there is no such wiggle here. And I wouldn't be mentioning this if it didn't produce something interesting, which is agreement. So for the M thermal is equal to 1 EV and delta N effective is equal to 1 case, we find that using the thermal speed produces better agreement between the simulation results and the HM code predictions. So this is interesting and requires a little bit more work to dig into the fundamental reasons as to why that they're agreeing with one another. And this leads us to the final slide, talking about our next directions. One such direction is investigating the actual definition of the particle masses in the simulations. Are we using M effective or are we using M thermal? Another is the actual fluid approximation, not of the reps code, but of the Boltzmann evaluations in class. Class has this wonderful suite of assumptions that one can turn on and off, and approximations one can turn on and off, one being the fluid approximations for neutrinos. We're finding in this limit, turning on and off the fluid approximation and taking the full evaluation of the Boltzmann equations can lead to fairly significant differences between the two, even for a thermal mass of 1 eV. On the left here, we can see the ratio of these power spectra, the fluid over the no fluid power spectra at z is equal to 0, and on the right, z is equal to 99. So even at this very high redshift, the fluid and no fluid approximations do not yet agree with one another. There are plenty of directions to look into. I'm very much looking forward to discussions with you all on this work, these preliminary investigations and possible solutions, and thank you for your attention.